Hello dear DP physics and other physics students, welcome back to Rubber Duck Physics. Today we are diving into one of the most famous experiments in physics history, the Michelson-Morley experiment. It's the story of how two determined scientists set out to measure the unmeasurable, and in doing so challenged the very foundations of classical physics. Before these experiments, scientists believed in something called the luminiferous aether, a substance filling the universe through which light waves were thought to travel. The aether was expected to provide an absolute resting frame, a kind of stationary backdrop for the entire universe. In the 1860s and 70s, James Clerk Maxwell had completed his groundbreaking theory describing the behavior of light as an electromagnetic wave. This theory predicted the existence of a universal speed of light, about 300,000 kilometers per second. But there was a problem. Maxwell's theory didn't specify a frame of reference for this speed. How could the speed of light be a single constant without an absolute resting frame? Michelson and Morley set out to answer this question with a groundbreaking experiment in 1887. Their experiment was designed to detect the aether headwind, the effect of Earth's motion through the supposed aether on the speed of light. Michelson and Morley built an enormous, highly precise interferometer. Light was split into two beams, set along perpendicular paths, reflected back, and recombined to form an interference pattern. How this pattern looks is covered in the DP physics unit about waves. At this point it is enough to understand that their setup was accurate to detecting shifts in the interference pattern corresponding to path differences of the light beams on the order of a fraction of the wavelength of light. If the Earth was moving through the aether, one beam should have been slowed down or sped up relative to the other, causing a noticeable shift in the pattern when the apparatus was rotated, the highest when rotated by 90 degrees. But, to their surprise and the surprise of the entire scientific community, there was no shift. The interference pattern stayed exactly the same, no matter how they rotated the apparatus or when they conducted the experiment. To ensure this wasn't just a fluke, the experiment was repeated in other locations and during different seasons of the year. The idea was to account for the Earth's changing motion relative to the aether, which might have placed the apparatus in a neutral position at the time of the first test. But the outcome was always the same, a null result. No aether headwind was ever detected, no matter where or when the experiment was conducted. The Michelson-Morley experiment revealed something remarkable. The speed of light appeared to be absolute, independent of the motion of the source or the observer. This result posed a direct challenge to the idea of absolute motion and the concept of a universal resting frame. It left scientists with a profound paradox. How could the speed of light remain constant while everything else, like velocities of all known motions, followed the intuitive rules of Galilean relativity? A completely new understanding of space and time was needed to explain the results. This would require abandoning some of our most basic intuitions about space and time and introducing a mathematical transformation that could reconcile these ideas. How can the idea of the speed of light seeming absolute, found in this experiment, be saved by a non-intuitive mathematical action? We'll answer this question in the next video with the Lorentz transformations. Let's quickly summarize what we have learned. Maxwell's theory predicted the existence and value of a universal speed of light. The Michelson-Morley experiment sought to detect the Earth's motion relative to the aether using a precise interferometer. The experiment and its follow-ups found a null result challenging the idea of absolute motion. This led to the conclusion that the speed of light is absolute, requiring a radical new interpretation of space and time. Before we wrap up, remember that I'm available to tutor students in physics and maths at the high school level. If you are studying A-level physics or maths, AP physics, IBDP or other similar physics curriculum and you would need extra support, I would be happy to help. You can find my email address in the channel data of the Rubber Duck Physics YouTube channel. It's visible only if you are using a browser on a computer, not in the app. Feel free to reach out. I would love to work with you. Thank you for watching Rubber Duck Physics. See you next time.